question is saying that answer the following. You can shield a charge from electrical forces by putting it inside a hollow conductor. Can you shield a body from the gravitational influence of nearby matter by putting it inside a hollow sphere or by some other means? So the answer to this question is no, because when it comes to the electrical forces, then charge plays a big role, and when the charge particle is put inside the hollow cylinder, a hollow conductor, then the charge rearrangement takes place, which act as a shield for the charged particle. And this is not the case with the gravitational force, as the body can't be insulated until or unless we make the gravitational potential zero, that is, put it at infinity of distance. The second question says that an astronaut inside a small spaceship orbiting around the Earth cannot detect gravity. If the space station orbiting around the Earth has a large size, can he hope to detect gravity? So the answer is yes, because as the spaceship is orbiting around the Earth, it is at a certain speed which is keeping it there on that orbital path, because the force is getting balanced over there and the body is at free fall. So the velocity of spaceship and the man is same roughly, and they both are in the situation of free fall, thus they can't feel gravity due to Earth. Whereas when the spaceship will have a large mass, then he will experience gravity due to the spaceship, because we know that gravitational force is equals to g mass of the man multiplied by mass of the spaceship divided by their distance of separation squared. Now when mass of the spaceship will become greater, then obviously the magnitude of force will become high, and when we compare it with the equation F is equals to mg, then obviously this g will be high to accommodate the higher force, so g will become significant. Now in third question we have, if you compare the gravitational force on Earth due to sun to that due to moon, you will find out that the sun's pull is greater than the moon's pull. Now however, the tidal effect of moon's pull is greater than the tidal effect of sun. Why? So there are a couple of reasons for that. The first is, moon is near to the Earth as compared with the sun, and sun intensify or diminishes the effect of moon over the tides. Now sun can play two kinds of role here, like if the sun and moon is in a direction in a line, then it will intensify the effect of tide on Earth, and if it is not assisting moon's gravitational force, then it will try to diminish the effect of tide of the moon. Thank you. The question says that choose the correct alternative. The first question is, acceleration due to gravity increases or decreases with increasing altitude. So we know that for the acceleration due to gravity at height h, the expression is g mass of the Earth divided by radius of the Earth plus height squared. Now as h will increase, the re plus h square term will increase, thus gh will decrease, and thus the acceleration due to gravity at given height will decrease as compared to that on the surface. So it will decrease. Now similarly, for the case of depth also it follows the same convention, like if the depth will increase, then the acceleration due to gravity as compared from the surface will decrease. Now in third, we have acceleration due to gravity is independent of mass of Earth or mass of the body. Now as we see from both of the expressions, we see here mass of the Earth in the equation. Now since it is dependent upon the mass of the Earth, so it will be independent of mass of the body. Now in fourth question we have the formula minus g mm 1 by r square minus 1 by 1 by r2 minus 1 by r1 is more or less accurate than the formula mg r2 minus r1 for the difference of potential energy between 2 points r2 and r1 distance away from the center of the earth. Now in this question we see that here acceleration due to gravity is taken as constant, so obviously it would be less accurate as compared with this expression, where it can be seen that it is not constant, so it is more accurate as compared to this equation. Thank you. The question is saying that suppose there existed a planet that went around the sun twice as fast as the earth, what would be the orbital size of the planet as compared to that of the earth? So the question is saying that the time period of that planet is half of that of the earth, or the time period of earth is twice of that of the planet. So we have to compare its orbital size. Now we know that the relation of time period and orbital radius can be given by t square equals to 4 pi square divided by ms multiplied with r cube. Here ms is the mass of the sun and g is the gravitational constant, r is the orbital radius. Now assuming that the time period of earth be te and time period of that other planet is tp, and orbital size of earth be re and orbital size of that other planet be rp. So while taking the ratio we can write it as this form. Now substituting te square with 4 tp square, as we have been given that 2 tp equals to te. Now reducing this ratio, we will get that the orbital radius of that planet is equals to 0.63 times that of the earth. So the planet is nearer to sun as compared to that of the earth. Thank you. The question says that Lu, one of the satellite of Jupiter, has an orbital period of 1.769 days and radius of the orbit is 4.22 into 10 raised to the power 8 meter. Show that the mass of Jupiter is about 1000 that of the sun. So we have been given that the orbital period of the satellite, one of the satellite of Jupiter, is 1.769 days and the radius of the orbit is 4.22 into 10 raised to the power 8 meter. So from this data we have to calculate the mass of Jupiter and we have to compare it with the mass of sun, and we have to show that it differs by the factor of 10 raised to the power minus 3. So let us first see that the force of gravitation when a body is like, this is Jupiter in the center and this is the satellite of Jupiter. So when a satellite is moving around, then it must be facing this force called gravitation towards the Jupiter, and centripetal force is towards the outer side. Now these two forces must cancel out each other so that the satellite will remain in the orbit. So gravitational force must be equal to the force of centripetal force. So from equating these two and from expression, we can find out the speed of this satellite as the perimeter of the circular orbit divided by the time period. So we can find out the velocity of this planet, of this satellite. Now using these two equations, we find out that the expression for mass of Jupiter is 4 pi square radius of the orbital radius of the satellite cube divided by gravitational constant multiplied with the time period of revolution squared. Now from that data we find out that mass of Jupiter is 1.9 into 10 to the power 27 kg. Now here time orbital period of this satellite is taken in seconds so that units are consistent. Now we know that mass of the sun is 2 into 10 to the power 30 kg. So dividing this mass of Jupiter with the mass of Sun, we get a factor of 10 to the power minus 3. So we can say that the mass of Jupiter is 10 to the power minus 3 times, or 1000th times that of the mass of the Sun. Thank you. The question says that let us assume that our galaxy consists of 2.5 into 10 to the power 11 stars, each of 1 solar mass. How long will a star at a distance of 50,000 light years from the galactic center take to complete one revolution? Take the diameter of Milky Way to be 10 to the power 50 light years. So we haven't given that there is a galaxy called Milky Way, and it has 2.5 into 10 to the power 11 stars, and each of the star is having 1 solar mass, and solar mass is defined as 2 into 10 to the power 30 kg, that is one mass of one sun. And we have to find out the time period a star would require to complete one revolution, and that star is 50,000 light years away from the galactic center. 1 light year is equals to 9.46 into 10 to the power 15 meter. So we have to find out time required to complete one revolution, and the diameter of this Milky Way galaxy is given as 10 to the power 5 light year. So we calculate the mass of galaxy, that is 5 into 10 to the power 41 kg, by multiplying this number of stars and one solar mass. And we also find out the radius of galaxy in meter. 5 into 10 to the power 4 light year, as the diameter is 10 into 10 to the power 5, so 10 into 10 to the power 4. So by dividing it by 2, we can get it 5 into 10 to the power 4 light year, and 1 light year equals to 9.46 into 10 to the power 15 meter. So it is 4.73 into 10 to the power 20 meter. Now the time period required by time period of one revolution is given by the expression as under root of this 4 pi square by 6 pi g gravitational constant divided by mass multiplied with orbital radius cube. So using appropriate values, here g is 6.67 into 10 to the power minus 11, and mass is the mass of galaxy, and radius is the radius of the distance of the star from the galactic center. We get the time period as 3.55 into 10 to the power 8 years. Thank you. The question says that choose the correct alternative. If the zero of potential energy is at infinity, the total energy of an orbiting satellite is negative of its kinetic or potential energy. So we have to say that if zero of the potential energy is at infinity, or if at infinity the potential energy is zero, then about orbiting satellite, its total energy is negative of what? Either kinetic energy or its potential energy. So before answering this question, we should know what is the kinetic energy of the orbiting satellite and what is the potential energy of the orbiting satellite. So from the equilibrium of force, the attractive force is balanced by the centripetal force of the satellite, and attractive force is the gravitational force, and the centripetal force is mv square by the distance of satellite from the center of Earth. Now if we find out expression of velocity from this expression, then we will get v square equals to g mass of the Earth divided by radius of the Earth plus height. Now we can use this v square in the kinetic energy of the satellite. Now kinetic energy is given by half mv square. Now half multiplying half m to this, we get gm mass of the Earth divided by 2 re plus h. Here small m is the mass of the satellite, and re is the radius of the Earth, and h is the height above its surface. H is the height of the orbiting satellite above the surface of Earth. And potential energy is given by minus g mass of the satellite multiplied with mass of the Earth divided by
radius of the earth plus height, or the distance of the satellite from the center of the earth. Now upon evaluating total energy, we will get minus gm me by 2 re plus h. Now this expression exactly matches the negative of the kinetic energy. Now we can say that the zero of potential energy is at kinetic energy, then the total energy of an orbiting satellite is negative of its kinetic energy. Now moving forward to the second question, we have the total energy required to launch an orbiting satellite out of Earth's influence is more or less than the energy required to project the stationary object at the same height out of Earth's influence. Now we have to compare the energy required to launch an orbiting satellite out of the Earth's gravitational influence and the stationary object at the same height of the orbiting satellite out of the Earth's gravitational influence. So here, out of the gravitational influence means that the minimum criteria for reaching of this condition is that total energy should become zero, because as far as it will be in Earth's influence, then it will have negative potential energy, because we know that attractive potential energy is always negative. Now we know the condition for going out of the Earth's influence, that is total energy should be equal to zero. Now case 1, where satellite orbiting with a speed v, let us assume that it is orbiting with a speed v. Now total energy of the satellite, as we calculated from the above equation, that it is minus gm me by 2 re plus h. So the energy required in this case would be just positive of this energy, because if we add this energy to the system, then it will have zero total energy and the satellite will be out of the Earth's gravitational influence. Now in case 2, we have object where the object is stationary at height h. Now the total energy is given by the gravitational potential energy, because it is not having any kinetic energy. Now if we compare these two energies, then obviously this energy is 2 times that of the energy in this case, the first case, or the energy of an object at a stationary height h is twice as that of the energy of the satellite orbiting with some speed. So we can say that in case 2, the energy required will be more, because it is more negative as compared to the first one, or the object which is stationary at height h requires more energy as compared to the satellite which is orbiting with the speed of some magnitude. So we can answer this question now, that the energy required to launch an orbiting satellite out of Earth's gravitational influence is less than the energy required to project a stationary object at the same height out of Earth's influence. Thank you. The question says that, does the escape speed of a body from Earth depend upon the mass of the body, the location from where it is projected, the direction of projection, or the height of location from where the body is launched? So here we must understand the concept of escape velocity. Now escape velocity is the velocity that must be given to the body so that it can get out of the Earth's influence, Earth's gravitational influence. Now the necessary condition for this is that the total energy of the body should be equal to 0. Now if we decompose total energy in potential energy and kinetic energy, then we can write kinetic energy as half mv square, where v is the velocity of the body that is to be given, or the escape velocity, and potential energy of the gravitation is minus gm, that is mass of the body, multiplied with mass of the earth divided by radius of the earth plus height, or the distance of that body from the center of earth. Now upon equating it with 0, we will get v equals to root under gmme divided by re plus h. Now here we see that the escape velocity, that is v, is not depending upon the mass of the body, so this is not the right choice. Now the second is the location from where it is projected, it is also not in the equation. In third, the direction of projection, it doesn't depend upon that. And the fourth is height of the location from where the body is launched. Now this h represents the height of the body from the surface of earth. So it does really matter what is the height. So it depends upon the height. So this option is going to be correct. Thank you. The question says that the comet orbits around Sun in a highly elliptical orbit. Does the comet have a constant linear speed? So there are various physical quantity that is given, and we have to say that which of the property are constant. Now when we assume that this is Sun and this is the comet and it is going in a highly elliptical orbit. Now I can't, it just got wrong. So let us assume that this is the highly elliptical orbit. It is looking like an ellipse. This is the comet. Now we have to say, we have to just choose which of these quantities would be constant throughout the motion. Now the first option is linear speed. We know that linear speed will change when it will go near as compared to when it will go farther, because according to the Kepler's law, the area traversed by the comet should equal in equal times. So obviously its linear speed is not going to be constant. It changes with the position vector. So this is not correct. Angular speed similarly will vary. Now angular momentum is going to be conserved, because if we consider these two system and these two as a system, then there is no any external forces acting, external unbalanced forces acting. So we can say that angular momentum is going to be conserved. Now the fourth option is kinetic energy and the fifth option is potential energy. So since this no net force is acting on this system, we can say total energy is going to be conserved, but we can't say that individually kinetic or potential energy is going to be conserved. So both of this option is not going to be true. Now in fifth option we have total energy throughout its orbit. Now this is going to be true, because net force on this system is negligible. So angular momentum and total energy throughout its orbit is going to be constant. Thank you. The question says that which of the following symptoms is likely to afflict an astronaut in space. So here afflict means affect, or we can say that which of these symptoms is going to affect the astronaut working, or it will affect its performance, we can say. So first is swollen feet. Now we know that the astronaut don't need to stand on its feet, or the gravitational force is not aligned oriented. So the astronaut is not going to stand, so the swollen feet is not going to affect much to an astronaut. So this option is not going to be correct. Now swollen face may distract him or her in working, so it can affect. Headache as well can affect his or her working, and orientation problem is one of the prime problem that the astronaut faces due to weightlessness. So this is obviously going to affect how they work, for which they are trained properly. So we can say these three symptoms is going to affect the astronaut in space. Thank you. The question says that in the following two exercises, choose the correct answer among the given ones. The gravitational intensity at the center of a hemispherical shell of uniform mass density has a direction indicated by the arrow. So it is talking about the center point, that is this C point, and we have to say what is the direction of gravitational intensity. Now gravitational intensity is defined as the force per unit mass of the body. So since it is the hemisphere, we can say that the mass is totally in the bottom side of this hemisphere. So obviously the force of attraction would be in the bottom side, and thus the gravitational intensity direction is in the bottom side. So for the point C, in the direction of C, it is going to have the gravitational intensity. So C option is correct. The question says that for the above problem, direction of gravitational intensity at an arbitrary point P is indicated by the arrow. Now at point P, since it is a hemisphere, the mass is in the bottom side, so its direction of force, gravitational force, is going to be downward for the point P. Now the gravitational intensity is defined as the force per unit mass, and its direction is in the downward direction as well, because the force is directed downwards. So the direction E is going to be true in this case. Thank you. The question says that a rocket is fired from Earth towards the Sun. At what distance from the Earth's center is the gravitational force on the rocket 0? Mass of Sun is 2 into 10 raised to the power 30 kg, and mass of Earth is 6 into 10 raised to the power 24 kg. Neglect the effect of other planets, and orbital radius of Earth is 1.5 into 10 raised to the power 11 meter. Now we have to actually find out the point of equilibrium where the rocket will be attracted by both Earth and Sun equally. Now that is the point where we will have gravitational force, net force on the rocket is 0. So let us assume that x is the distance of the rocket from Earth's center, and r is the distance of Earth from Sun. Now we assume that me is the mass of Earth and ms is the mass of Sun. Now distance of rocket from the Sun is r minus x. Now we equilibrate the force in both the direction. We will get that g, mass of the Earth, times mass of the rocket divided by x square, or the distance squared, is equals to g times mass of the rocket times mass of the Sun divided by r minus x square. Now upon solving this, we will get x, or the distance of rocket from the Earth, to be about 2.6 into 10 to the power 8 meter. So the concept that we used in this question was the force equilibrium, that is equating the force of Earth and force of Sun on the rocket, and we got the value of x as 2.6 into 10 to the power 8 meter. Thank you. The question says that how will you weigh the Sun, that is estimate its mass? The mean orbital radius of the Earth around the Sun is 1.5 into 10 raised to the power 8 kilometers. So we have to estimate the mass of Sun here, and given that the orbital radius of Earth around the Sun is 1.5 into 10 raised to the power 8 kilometers, or 1.5 into 10 raised to the power 11 meters. Now we know the relation of time period and orbital radius of planet around the Sun, that is related by t square, that is time period square, equals to 4 pi square divided by gravitation constant, mass of the Sun, multiplied with radius cube, orbital radius cube. Now using this relation, we have time period known, that is 1 year, and the orbital radius is known, that is 1.5 into 10 to the power 11 meters. Now only ms here is unknown, because this is the gravitational constant that we'll be using. So ms can be estimated by this relation, and it is calculated to 2 into 10 to the power 30 kilogram, or 1 solar mass. Thank you. The question says that a Saturn year is 29.5 times the year of Earth. How far is the Saturn from Sun if the Earth is 1.5 into 10 to the power 8 kilometers away from the Sun? So here we have been given the comparison of the Saturn and planet Earth, which both revolve around the Sun, and one has a time period of 29.5 years as compared to Earth, that is Earth is having a time period of 1 year. And now orbital radius of Earth is 1.5 into 10 to the power 8 kilometer, or the center of Earth is 1.5 into 10 to the power 8 kilometer away from the center of Sun. Now we have to estimate the distance of Sun center and the Saturn center. So we'll be using again that relation of time period and orbital radius. Now since we have been given a comparison of two different planets around the same Sun, so we'll be taking the ratio of both. Now in this ratio, mass of the Sun, this constant g 4 pi square divided by gms is both constant in both the relations. So this will be, the ratio of this will be equal to 1. Now we'll be left with time squared, the ratio of time squared, and the cube of the orbital radius. Now here t represents the time period of Earth, and r represents the orbital radius of Earth, and ts is the time period of Saturn, and rs is the orbital radius of Saturn. Now here we have been given the time period of Earth, that is 1 year, and time period of Saturn, that is 29.5 years, and orbital radius of Earth is given. Now only rs is unknown over here. So upon calculation we will find out that rs can be calculated to about 1.4 into 10 to the power 12 meters. Now here we don't need to convert this time period in second, because they both have same unit and we are taking ratio, so it doesn't matter to be converted. We can simply use 1 and 29.5 squared. So we see here that Saturn is, the distance of Saturn from Sun is like 10 times more than the distance of Sun from Earth, as the Earth is 1.5 into 10 to the power 11 meters away from Sun, and Saturn is 1.4 times 10 to the power 12 meters away from Sun. Thank you. Question says that a body weighs 63 Newton on the surface of Earth. What is the gravitational force on it due to the Earth at the height equal to half of the radius of Earth? So we have to compare the weight on the surface as well as the height, that is equal to half of radius of Earth. That is, if we assume the radius of Earth to be re, then h at height h equals to re by 2. What is the weight of this body? So we can simplify this question by finding out the gravitational constant, acceleration due to gravity at height equal to radius of the Earth half. Now we know that force of gravitation equals to g, that is gravitational constant, times mass of the body, that is our test body, and mass of the Earth multiplied divided by the distance of separation between them, that is radius of the Earth plus height h squared. Now this will be equal to mass of the body times acceleration due to gravity at height h. Now since these both mass are equal, so the ratio of them will be equal to 1. Now acceleration due to gravity, gh, will be g mass of Earth divided by radius of Earth plus h squared. Now here h is equals to re by 2. So now we have this relation gme by re plus h squared. Since h is equals to re by 2, then simplifying this we get 4 by 9 times gme by re square. Now at surface we know that mass of the body times gravitational acceleration to gravity equals to gm mass of earth divided by r radius of the earth squared. Now this relation is valid on the surface of earth as height is equals to 0. Now at this time we see that g is equals to g me by r square, that is this value. Now this we can replace with acceleration due to gravity, that is 9.8 meter per second square. Now since we know that g me by r square equals to g, so gh will be equal to 4 by 9 times the g at surface. So if acceleration due to gravity at height h is equals to 4 by 9 times the acceleration due to gravity at the surface of earth, that's how we can relate the weight of the body at height re by 2, and that will be equal to 4.9 times that of the weight of that body on the surface of earth. So it is calculated to be about 28 newtons. Thank you. The question says that assuming the earth to be a sphere of mass of uniform density, how much would a body weigh half down to the center of earth if it weighed 250 newtons on the surface? So what happens is that let us assume that this is earth, and as we go deep below, now since we have been given that it is of uniform mass density, that is the density of the earth at any point would be constant. So let us assume that we have reached here. Now let us assume that this is the sphere that is on the surface of this, the particle is on the surface of this imaginary sphere. Now we know that at any point on the surface, the gravitational force due to the outer sphere on the particle, let us assume that the particle is here. Now the gravitational force due to this outer sphere would be equal to 0 at this point. So the only gravitational force that would be acting on this particle would be because of this mass. Now since it is having a uniform mass density, so we can calculate the mass of this inner sphere. So upon calculation, we can simplify this using the acceleration due to gravity. That is, acceleration due to gravity at depth d will be equal to g times, that is the acceleration due to gravity at the surface of earth, times 1 minus d, that is the depth, divided by radius of the earth. So we have been given here depth, that is equals to radius of the earth divided by 2 or the half of the radius of earth. So upon using this relation, we will get that at height half of that of the radius, we will be having gravitational acceleration to gravity half. So since acceleration due to gravity will be half at this depth, so the weight would also be equal to half of the weight at the surface. That is, if at the surface the body is being weighed, body has a weight of 250 newton, then at the depth of half of that of the radius of earth, it will weigh 125 newton. Thank you. The question says that a rocket is fired vertically up with a speed of 5 km per second from Earth's surface. How far from the Earth does the rocket go before returning to Earth? Mass of the Earth is given, mean radius of the Earth is given, and gravitational constant is given. Now in this question, what we see is that Earth and rocket system is isolated, or we can say that there is no any net force, unbalanced force is acting on it. So the total energy initial is going to be equal to total energy final. So here kinetic energy initial is the half mv1 square vi square, where vi is the initial rocket speed, that is 5 km per second. Now potential energy at the surface of earth is minus gmm by radius of the earth, Now this will be equal to final kinetic energy plus final potential energy. Let us assume that the rocket goes at height h, so its final potential energy is going to be minus gm_me divided by re plus h, that is radius of the earth plus height h. So now at the highest point its velocity is going to be 0, because that is the highest point over which the rocket will go. As we see that how far does the rocket go before it returns to earth, that is its velocity is going to be 0 at that point. Now upon solving this is going to be 0, this quantity vf. Now upon solving this for h, we will get h, that is equals to 8 into 10 to the power 6 meter. So the rocket will go up to about 8 into 10 to the power 6 meters, and then it will turn back to earth. Now since this rocket is not having adequate speed for its escape out of the earth's gravitational influence, so it is not going to escape and it is going to return back to earth. Thank you. Question says that the escape speed of a projectile on the Earth's surface is 11.2 km per second. A body is projected out with the thrice of this speed. What is the speed of the body far away from Earth? Ignore the presence of Sun and other planets. So here we have been given a body and Earth as a system, and it is given that the escape speed of a projectile on Earth's surface is 11.2 km per second. That means if this much velocity is given to an object on Earth, then it has the energy to escape the Earth's gravitational field, or this is the necessary condition for a body to go to a place where Earth's gravitational influence would be 0. Now the necessary condition of the escape velocity, or the body going away from Earth, or the body going away from the influence of gravitational force of Earth, is its total energy should be equal to 0. Now if this much velocity is given to the body, or this much speed is attained by the body, then its kinetic energy would be half into mass into velocity of escape square plus its potential energy on the surface. Now this will sum up to be equal to 0, because this is the necessary condition for the body where it can be assumed that the body has escaped the Earth's gravitational influence. So let us represent the VESC as the escape velocity and the velocity of projection to be Vp, that is 3 of VESC, and the final velocity that the body is having is V final, since the body is projected with thrice the speed of escape velocity. So applying the conservation of energy principle, the kinetic energy initial plus potential energy initial must be equal to kinetic energy final plus potential energy final. Here initial state refers to the state where the body is on Earth's surface, and the final state is where the body is out of the influence of gravity. Now since its initial velocity is 3 times the velocity of escape, so it can be written as half m 3 VESC squared plus potential energy, that would be equal to half m times Vf, that is the final velocity squared, plus 0 potential energy. Since it will not be having any effect of gravitational force when it escapes its influence, so the potential energy would be 0. Now since we know that potential energy initial plus half mv ESC square would be equal to 0, as this is the primary condition for escape velocity, so using this third relation, in the second relation we can get that 4 times mass into velocity of escape squared is equal to half mvf square. Now this has been reduced, this relation has been reduced from this relation by nullifying this term from this left hand side of this equation as P potential energy initial plus half of this half mv escape square. We have eliminated this. Now we will get 4m v escape square equals to half m vf squared. Now vf would be 2 root 2 times v escape, or it is 31.67 kilometer per second. Thank you. Question says that a satellite orbits the Earth at a height of 400 km above the Earth's surface. How much energy must be expended to rocket the satellite out of the Earth's gravitational influence? Now mass of the satellite is given, mass of the Earth is given, and the radius of Earth is given. Gravitational constant is given. Now here we must understand that it is asking how much energy does we need to expend on the rocket so that it can move the satellite away from the Earth's gravitational influence. Now the necessary condition of moving the Earth's gravitational influence would be to take the energy level of the satellite to zero, total energy of the satellite to be zero. Now since it is orbiting the Earth, it is under the influence of attractive force, so its total energy must be negative. Now there must be some positive energy that we should expend on the rocket so that the total energy would be zero. Now let us find the total energy of the satellite while orbiting. So it would be equal to the sum of kinetic energy and its potential energy. Now we have the expression for the same, like it is minus of half of gmme, mass of the Earth, times mass of the satellite, divided by re, that is radius of Earth, plus height, or the distance of the satellite from the Earth's core. Now this comes to be about minus 5.9 into 10 raised to the power 9 joule. Now this is attractive, hence it is in minus negative sign. So we have to expend this much of positive energy to turn this total energy of the satellite to zero. Now so we need to expend 5.9 into 10 to the power 6 joule so that the total energy becomes zero and the satellite will be thrown out of the Earth's gravitational influence. Thank you. The question says that two stars, each of one solar mass, are approaching each other for a head-on collision. When they are at a distance of 10 to the power minus 9 10 to the power 9 km, their speed are negligible. What is the speed with which they will collide? The radius of each star is 10 to the power 4 km. Assume that the star to remain distorted until they collide. So here these two stars are not being acted upon by net external force, so the total energy of both the stars is going to be of the system is going to be conserved. That is, total energy initial is going to be total energy final. Now here are a few nomenclatures that we have used. Here small r represents the initial separation of the stars, and the capital R represents the radius of the star, and small m represents the mass of the star. So the initial condition is like this: both of the stars are far away distance, that is at r distance. Now after some time they will collide, and now the distance between their center would be equal to 2r on collision. So we have to determine what is the velocity that will be attained by both of the stars when they are about to collide. So here initial time frame represents the stars at the distance of r between them. Now the total mechanical energy initially is going to be equal to minus of gmm by r, because the it is fully composed of potential energy, because the velocity or the speed initially is going to be 0. So total mechanical energy initially is minus gmm divided by r. Now final mechanical energy is going to be composed of the velocity, the kinetic energy of both the stars, that is half mv square plus half mv square. We have assumed both to be of the same velocity, plus potential energy, and potential energy would be equal to minus of gmm by 2r, as the minus of gmm is the product of the both of their masses, and their separation of their center is 2r, so it is minus gmm by r. Now upon solving this for v, we will get velocity to be equal to 2.58 into 10 to the power 6 meter per second. So when they are about to collide, their velocity is 2.58 into 10 to the power 6 meter per second. Thank you. The question says that two heavy spheres, each of mass 100 kg and radius 0.10 meter, are placed 1 meter apart from the horizontal table. What is the gravitational force and potential at the midpoint of the line joining the center of the sphere? Is an object placed at the point is in equilibrium? If so, is the equilibrium stable or unstable? So we have two spheres, both of 100 kg mass and radius of 0.1 meter. Now they both are separated by a distance of 1 meter. We have to find out force and potential at this midpoint. So force, as far as force is considered, the force from the left sphere and the right sphere is going to cancel out each other, and the net force on the particle is going to be 0, because both of the spheres are of same mass and same radius, and the distance of separation is also same. So as we see over here also, that they both will cancel out. Now potential energy, now we have to calculate potential at the midpoint also. So potential is defined as the potential energy per unit mass. So it would be minus gm by r by 2, where r is the distance of separation. So here r is the distance of separation. Let us consider that this is r. So r is the distance of separation. Now this is r by 2, so it is 0.5 meter. Now when we calculate this, we will get value of minus 2.67 into 10 to the power minus 8 joule per kg. Now the third question is, if so, if the body is in equilibrium, and we see that the force is 0, so body is in equilibrium, though, so it asks, if so, is the equilibrium stable or unstable? So we see that when we displace this body, then it will be displaced and the body will lose its equilibrium. So it is in unstable equilibrium. Now if it was in stable equilibrium, then upon displacement the body would itself attain the same stable position. Like, let us consider this ball. So if a ball is here and it is in stable equilibrium, now if we displace this ball, keep it over here, then it will swing on its own to reach here. Now this is called a stable equilibrium. Now in the other case, if the ball is on the dome, now if the ball is here and if we displace the ball will fall down and it will never be able to reach over here on its own. Some work has to be done on this ball to make it reach here. So this is called unstable equilibrium. So the body is in unstable equilibrium if it is over here. Thank you.